When I was trying to pay.
Okay, so here's what we got today. We're going to go over this concept of limiting reactants and percent yield. Because we have to do that to do some of the calculations for the lab. And we'll as soon as we get done with that, we'll go in, and this lab takes like 2 days. Because some of the reactions you have to start today, they have to run, and then you've got to like do some evaporations and things like that, which we'll finish up on Monday. So here's kind of your sequence. So last topic today, limiting reactants, we'll go over that. Start the lab today, finish the lab on Tuesday, finish the lab on Monday, review on Tuesday, written final Wednesday, and then lab final will be Thursday, Friday, Monday, Tuesday, Wednesday. So if you want to plan ahead, that's kind of what we're looking at. Now, here's the whole key on limiting reactants, is that the first thing you have to do is determine if it's a limiting reactant problem, okay? So let's say, for example, in the lab that you're going to do, you're going to take, say, for example, sodium chlorate, and you're going to decompose that into sodium chloride and oxygen gas, okay? CO3. So right away, is this going to be a limiting reactant problem? Why not?
There's only one reactant.
Yeah, you only have sodium chlorate. This reaction goes until you run out of sodium chlorate. So there isn't two things that can run out. Okay, this is like you taking cheese sandwiches and breaking them up into bread and the cheese. Okay, Miles can do that until he runs out of sandwiches. As soon as he runs out of sandwiches, okay, hey, we're done. So decomposition problems are never limiting reactant problems because they just go until it runs out. So first off, you can only have a limiting reactant problem when you have two different reactants. Now, if you look on, somebody had asked about number 4 on that last page, or on the back side, right? So you've got magnesium, I pinned that one right, magnesium reacting with nitrogen. Oh, I hate my pen today. Turning into Mg3 N2. Okay? You're going to make magnesium nitrate. So, what type of reaction is it? You're taking two things and making them into one.
Synthesis.
It's a synthesis reaction, right? Decomposition would be if I took it and separated it, broke it apart.
Wait, which one are we on? Were we on the top one?
We're on this one,
Oh, sorry. I was looking
okay?
at
We're on this one. So, here's the deal. So, if I had just said you had 63 grams of magnesium, okay? And let's say that's all I gave you, which is 63 grams of magnesium. And said, hey, what's the yield of your magnesium nitride? If that's all I gave you, it wouldn't be a limiting reactant problem. Because what you would assume, and you'd have to because you don't have any other information, you just have to assume that this reaction is going to go until the magnesium is used up and you have an excess amount of nitrogen. Okay? That's the only thing you could do. Is it. It's just say, okay, hey, I got the 63 grams of magnesium. As soon as this runs out, the reaction stops. But if you look at the problem, you're given information about the magnesium and the 41 grams of nitrogen. Okay? So as soon as you have information about both reactants, then you have to go, oh, this is a limiting reactant problem. Okay? So that's one of the key things. Like, ask yourself this. Do you have information about two of the reactants? If you do, right away, you have to take this all the way through to the end. Now, here's a common mistake that I've seen on some of your papers. You have 41 grams of N2. So, you got grams of N2, you're going to put grams of N2 here, you're going to put, I got to get a new pen. 1 mole of N2 up here. Now, here's the deal. When you do this, because this is diatomic, don't put 14 grams down here. You have to put 28 grams because this is N2. It's a diatomic molecule. You have 2 nitrogen atoms hooked up. So this needs to be 28 grams, not 14. So on that assignment that I just gave back, it was like oxygen, which is diatomic, and you were putting 16 grams instead of 32 grams. So when it's diatomic, you have to double up that relative atomic mass because there's 2 of those hooked together. So here's the story. So when you get on number 4, you're going to figure out how much Mg can be made from the magnesium, and that should be around 90 grams. Okay, so you should be able to make about 90 grams of Mg3N2 from the mass of the magnesium. And then from the nitrogen, you should be able to make about 150 grams. Okay, so those are roughly going to be your 2 answers on number 4. So then if you go to that analogy that we talked about yesterday with making the cheese sandwiches, if Miles can make 5 sandwiches from the cheese and he can make 8 sandwiches from the bread, he can only make 5 sandwiches. So you always pick the smaller amount. So the mass that you can produce is going to be the smaller of those 2, which is going to be about 90 grams. Okay? So then the actual yield is 80. So in other words, we run this experiment. Okay, this is one of the things you're going to do in the lab today. You're going to run this experiment. Okay, cool. You actually get 80 grams. You should theoretically get about 90. So your percent yield is take the amount that you got and divide it by what you should get. Typically, your percent yields are less than 100. If you actually get more than what you should have, your percent yield would be above 100%. That's like extra credit. Congratulations, you created a mass. Kind of cool. Usually it's less. So, on number 2, you don't have to take it all the way to grams because of the fact that all you're trying to figure out is which one's going to produce the smallest amount. So what you should see on number 2 is that 2 of the 3 are the same answer in terms of which one's the limiting reactant. Okay. Are we good with that? Anything at all you want me to go over on this concept of limiting reactant problems? Going once? Going twice? So, okay. So Miles, stop your number camera. All right. So here we go on your last lab other than the lab final. So this is going to combine a whole bunch of different things that we've talked about. So you have 2 distinct bits of information. You have one which is nothing but the instructions. Okay? So this is all this first packet, all this is telling you what to do. Okay? The second one is what you're going to hand in. Okay? So this is where you can do all your calculations, all the equations, all that good stuff. Now, this is like your culminating lab. I want to be impressed. So help me. If you do something like this, oh, here's my mole conversion, 14 to 1, I'm just going to quit grading your entire lab at that point. Okay? I swear to God, I'm just not even going to grade it. I'm just like, I have failed you, I'm just going to stop. Okay? This is your culminating lab, practical for equations, stoich, formulas, the whole thing. Okay? I want to see every label on every calculation. You want to be able to hand this to me and go, Mr. Brookham, I am proud of what I've done. You've taught me well. Here's what I've learned. Here's all your calculations. Be happy with this. Okay? I don't want to have to sigh loudly as I've been accused of doing this morning already. Yeah. Okay. So, I'm going to kind of give you the big picture on all of these, because some of these, like, you can start today and get done today. Some of this, you're going to start today, we won't be able to finish up until Monday. So the certain ones you want to get started today, once you get those started, then you can work on the other ones. Okay, so let me kind of get you through what's going to happen first. So on the first one, you're going to do what we call almost like a small scale titration. On a titration, you mix typically acids and bases together until it neutralizes out. Okay, so it's a standard kind of thing. Typically, you do it with big burettes. We're going to do it with small scale. We're going to use little dropper bottles. So you're going to get 8 drops of, so here on the instruction side, you're going to get 8 drops of 1 molar sulfuric acid. So in your well plate, you're going to put 8 drops. Okay, exactly. Then you add a little bit of phenolphthalein. Okay, phenolphthalein is great because of the fact that it turns magenta into basic solution. So you're going to have 8 drops of H2SO4. Then you're going to begin to add to that 1 molar sodium hydroxide, and then you're going to give it a little bit of a shake. And as you add more and more of that sodium hydroxide, it's going to neutralize more and more of that sulfuric acid until the last drop turns that color a magenta color. So, and literally it will come down to 1 drop. So what you'll see is that that magenta color lasts a little bit longer, and you've just kind of got to give that a little bit of a stir so that mixes around. So you want to count the drops of sodium hydroxide it takes until you just get that magenta color where it stays. Okay? And like I said, this is a small scale titration. Typically you do this with like big burettes, okay? And it's a bigger volume. It's the exact same idea. So any titration, you mix an acid and a base. And so what we do, the function of the phenolphthalein is that it's a color indicator when the titration is done, okay? We could use pH probes, we could measure that. We're just going to use phenolphthalein. So as soon as that color remains magenta colored, you know it's done because now it's gone a little bit basic. You've used up all the sulfuric acid. There you go. So that's one that you've got after that. Now, when you get to activity 2, this is one that you're going to start today, but we won't finish up until Monday. Okay? So with this one, what you need to do, so you're going to have your penny. And the reason that it has to be minted after 1984, like for example, here I've got one from this year, 2022, okay? So the change that happened was that prior to 1984, all the pennies were solid copper, okay? Solid all the way through. But what happened is that the pennies began to cost more to produce than what they were worth if you kept them as solid copper. So what they did, and this is what the reaction you're going to do. So now the pennies have a zinc core to them, okay? And that's what we have to get to. So we have to get to the zinc that's inside of it. Well, the copper itself, if you put the copper in hydrochloric acid, nothing's going to happen because copper is less reactive than the hydrogen is. So we put this in there and then it said, oh, nothing's going to happen. Well, that was exciting, okay? So what you're going to do is we have to expose the zinc to the acid. So what you're going to do, I don't have this, just take like a piece of sandpaper, okay? And if you do that and kind of rub that around, what you'll see is that that copper comes off and you'll see an exposed seam of zinc on the inside. So you don't have to go, what you want to do is, ideally, don't scratch like the flat surfaces. You just want to get and expose that around the edge. Because what we want to do is, what we want to be able to recover is the copper from that and the zinc, and only react the zinc that's inside of this. So take a piece of sandpaper, just go around like this, and it doesn't have to be completely shiny. Just go around like this, boom, there you go. Now, with this, there are certain, and you got to go back and forth between the two of them. So on this one, when I say the original mass of the penny, that is after you have scraped the edge so that you can expose that zinc. Now, the final mass of the penny, you won't be able to get this data, and that's why I've got this asterisk on there. We won't be able to have that information until day 2. So what you're going to do is that you're going to take this and you're going to measure out 25 milliliters of 6 molar hydrochloric acid, pretty concentrated stuff, okay? And now, notice this on this, I say 25 milliliters. Notice I don't say 25.00 milliliters. You need about 25 milliliters, okay? Because basically what we want to do is let the zinc be the limiting reactant. We want to have a whole bunch of hydrochloric acid. We want to make sure that all of the zinc gets reacted. So that's why we overload this thing with hydrochloric acid so the reaction's going to stop and get done. So what's going to happen is that you're going to put this in a beaker, okay? And when you come back on Monday, what you should see are just the copper that's here. And all of the zinc has reacted and turned into zinc chloride. So then what's going to happen on Monday, then we're going to take those pieces of copper that haven't reacted. I want to find the mass of those by themselves. That's how you're going to get the mass on this one. This is where you're going to get the final mass of the penny. That's what's going to be left over after the zinc has reacted. So you're going to have the original mass, you're going to have the mass of the copper that hasn't reacted, and then from that, you're going to be able to get the mass of the zinc. So that's why I said that, like for example, that data, you can't get that data until you come back in on Monday. Then what you're going to do on Monday, then we're going to take that solution that contains the zinc chloride, we're going to put it into an evaporating dish, and then we're going to heat it up, and we're going to boil off all of the liquid, so then we get the zinc chloride that's left behind, and then we'll be able to say, oh, okay, here's our theoretical yield of zinc chloride, here's the mass of zinc chloride after we get done. So that's why I said some of these you won't be able to finish all the calculations until you get to the data on Monday. Okay, so that's the second one. So that's the one that you have to start today so that you have that reaction going for Monday. Now, on the third one, this one you're going to take potassium chloride and you're going to decompose it. This is a one-time thing, okay? With this one, you're going to set this at a 45-degree angle, and this is the one that I've shown. We've done this before. I did it here, right? We had the burning wood splint. So you're going to put that potassium chloride in there. You're going to add somewhere between 2 to 3 grams. Okay? Whatever. Just something around there. Just make sure that you record that number. So then you're going to hold it at a 45-degree angle. Test tube clamps, hold it at about a 45. Put it in the Bunsen burner. And you're going to heat it pretty solidly for about 5 minutes. So you want to break the bonds that hold that potassium chloride to the oxygen. You're going to boil this stuff off. Obviously, you should see a decrease in mass. So with this one over here, on activity number 3, keep track of what you want. You want the mass of the test tube by itself, and make sure that this test tube has a white label on it, okay? Because that means it's Pyrex, that means it can withstand the heat. So you're going to get it, then you're going to put the potassium chloride in there. Then you're going to find the mass of the test tube and the potassium chlorate. Then from that you can figure out the mass of the potassium chlorate. Oh, subtract the 2. Boom, there you go. Mass of the test tube after you heat it. Then from that you can figure out the mass of the KCl that's still in the test tube. And then you can figure out the mass of the oxygen that was lost. So this one, that whole thing takes about 5 minutes. But there's nothing to continue on. That's just a one-time thing. Now, when you get to activity 4 is another one that we're going to start today, and we're going to finish up on Monday. So 2 and 4, what I would recommend as soon as you get into the lab, I'd get 2 and 4 going, and then go back, and then if you have time, you can do 1 and 3. So what's gonna happen on activity number 4, this is gonna be a single displacement reaction. So you're gonna get a 100 milliliter beaker, not a big deal. You're gonna measure out 6.20 grams of copper sulfate. Okay, now this one I'm gonna tell you exactly how much mass that you want. With the potassium chloride, I said, hey, something between 2 and 3 grams, whatever, something doesn't matter. This one, I want exactly 6.20 grams. Okay, that's why I said, hey, 6.20. Then you're going to add 50 milliliters, okay, of distilled water. Then you're going to measure out 1.12, and again, this is an exact amount. Then you're going to measure out 1.12 grams of iron filings. And with this lab, because remember, iron can be Fe2+, iron can be Fe3+. This is going to be Fe2+. Okay, so when you're doing all the equations to balance the chemical formulas and everything, this is going to be Fe2+. Not Fe3+, Fe2+. Okay, because that's why I want to make sure everybody knows exactly what's going on. This is also going to be copper 2 sulfate. Okay, not copper 1 sulfate, this is going to be copper 2 sulfate. So, what you're going to do is you're going to heat this up. So you're going to heat up the copper 2 sulfate and the water. The reason that we heat it up is because we want this reaction to take place rapidly. That's the reason that's the only reason that you heat this thing up. But don't let it boil. So you're going to have a hot plate, get out the hot plate, put it on there. You don't have very much liquid, so this stuff is going to heat up pretty quickly. So, stir it, get it to dissolve. Then you're going to add the iron filings to the warm solution. Again, what's going to happen is that the only reason that we heat this up is so that it happens rapidly. Okay? We could let it sit there and do this, but it would take forever to do. By heating it up, the reaction takes place more quickly. There you go. Now, you're going to let it sit there. When it asks you to decant a liquid, okay, here's what happens when you decant a liquid. So, you're going to have your 100 milliliter beaker. You're going to have a liquid in here with a solid at the bottom. What happens when you decant a liquid is that you take this, you use your stirring rod. Pretend this is your glass stirring rod, not a test tube. But what you do is you hold that over that like this. And so what that does is it acts like a dam. And it prevents the solid from flowing out. Okay? Some people like to do it like this. Some people like to hold it crossways like this. Okay? Doesn't make any difference. So when you're told to decant a liquid, all you're doing is that you're taking a stirring rod or something, typically it's a stirring rod, and you're just acting like you're just using that as a dam to slow down the fluid so that you keep that particulate matter behind it. So what you want to do is that you want to get to a point where in the bottom of this beaker, you're going to have like a wet residue. That's what you're going to let dry over the weekend, and then on Monday, we're going to weigh this after it's dried. Okay? So, here's what you want to make sure that you get done. You want to get the penny soaking in the hydrochloric acid. That's all you can do today. Get the penny soaking in the hydrochloric acid. That's all you can do. Activity 4 with the copper sulfate and the iron, that reaction has to be run. You have to pour the liquid off so that it can sit there and it can dry. Okay? Cool with that. Now, we're in there, you all know the drill. This is going to be dealing with some potentially nasty stuff. With that 6 molar hydrochloric acid, you're going to be heating up potassium chlorate. Stuff could potentially fly around. Make sure that you are wearing safety glasses. Okay? All right, so let's go do science.